Welcome. Thank you guys for turning up. I wasn't sure if 10 people would come, so I'm glad that more than 10 people came. I probably didn't pick the best title for what I'm describing. My colleague referred to it as cerebral, so I'm glad that didn't put too many of you off. Before I start, I want to point out that I've been a lot of talks where people have talked about making all this stuff open source. All of the stuff I talked to you about today and a bunch of other Solr plugins that we've built at Dice over the last couple of years, they're all available on GitHub right now for you to check out. The sort of container is Dice Tech Jobs, although GitHub Search doesn't seem to be smart enough to pick that up. So if you want to grab that URL, if you're interested in checking it out. We built a number of Solr plugins over the years. One is a custom MLT handler that allows you to do a lot of extra stuff that the regular MLT doesn't do. One of those being you can apply function boosts or boost functions to boost your output. So you can do kind of location-based matching and boosting. You can do content-based queries. You can do recommendations based on multiple documents. That's all in the MLT handler. We have a custom spell check plugin that allows you to inject your own spell check corrections before the Solr ones. It's very simple, but we found it very useful because Solr can only search an edit distance of 2. And so a lot of the most common typos we have are worse than that. So by injecting your own, that can help give you better spell check corrections. So go there, check it out. If you have any questions or any bugs or anything, just post them on the issues log. OK, so let's get to the talk. So I'll be talking about conceptual search. And what that is in a nutshell is how to get relevant matches to your query, even if none of your query terms appear in a document. Who am I? Well, I'm the chief data scientist at Dice.com. I work on a data science and analytics team headed by Yuri Burkov. And we've done a number of projects in the 2.5 years I've been there. A lot of them involve Solr. So we've built custom recommender systems that leverage Solr. We built a custom MLT handler that is fully available. We've used Solr to do did you mean functionality, which is spell check correction. We've done type aheads based on title, skills, and company. All of those are on the site right now. I've also been working a lot improving the relevancy of our algorithms on our job search site. So we switched to Solr last December. And we found big increases in accuracy and performance and so on. But as you all know, relevancy is an ongoing process, and so we're continually looking at algorithms and improving it, and I'm the sort of lead on that project. Some other things I worked on at Dice.com are our skills pages. So this is something we released a few months ago. If you go to dice.com/skills, you can look up technology skills on the site, such as Lucene or Solr, and you can get some interesting information about them. So this is a page for Apache Lucene. So at the top here, it shows you the most related skills to Lucene, in this case, Apache Solr, search engines, and Elasticsearch. Those kind of associations have been learned using algorithms that I will talk about in this talk, although that is not the goal of the talk. We also have a hierarchy of skills that have been built with one of our partners. You'll see that on here. You'll see trends of the skill over time, related jobs, and so on. There is a Solr page, very similar. So what Dice does, I should mention, if you haven't heard of us, we are the most popular technology-focused job board in the US. So we serve IT jobs, and so if you're looking for a technology job, Dice posts those jobs, and we also take people's resumes and allow employers to search them. OK, so enough about the company. I want to get on with the actual talk. OK, so before I talk about what conceptual search is, I want to talk about why this is important. Why would you care? So when I was trying to think about how best to explain this, really what I came down to was this. Like, there was one big relevancy tuning mistake or a limitation that I see a lot of companies have. We have a lot of sites, not just Dice.com, that are owned by my company, and so I've worked with a lot of these different sites. And they all kind of have the same challenges with doing relevancy tuning. And in my mind, that is most people ignore the importance of recall. And there's good reasons for this, because it's very hard to actually tune your algorithms for recall. So what is recall, if you don't know? So there's many metrics that people use to evaluate search engines. But the two most important ones that most people care about are precision and recall. Those are often combined as the F1 measure. And what precision is very easy to explain. It is the percentage of the search results you get back for a given query that are accurate or correct. So most relevancy tuning efforts and most relevancy tuning metrics, search evaluation metrics, really look at precision. People run a query, they look at what documents come back that are not relevant to the query, and I spend a lot of time trying to tune the query to correct those documents. I've seen a lot of talks today where they talk about that. Okay, what precision doesn't capture and what recall does capture is recall captures the documents that you don't get back from the query, right? So you can spend all day trying to tune your search engine, your search algorithm to improve the precision of your algorithm, but it doesn't help it match documents that don't match your query. And the reason that's really hard is because to really accurately measure recall, you need to go through your entire document set, figure out for a given query which of all those documents are relevant, and then build some kind of metrics around that. So for most practical applications where you have hundreds, thousands, or millions of documents, that's really kind of unfeasible. So while I'm not going to tell you how to automate or fix that issue particularly, what I am going to focus on is trying to use automated manners, automated mechanisms to improve the recall of your search engine without hurting precision. So what is conceptual search? And what does this have to do with recall and improvement recall? It also goes by the name of semantic search. The key idea behind conceptual search is that rather than doing keyword matching, so rather than relying on keywords in a document to match exactly the query terms, conceptual search tries to learn concepts that are important in your domain. These are concepts, ideas. These are very intuitive to people, but it's extremely hard to get an algorithm to do this. And so rather than match over exact keywords or synonyms, conceptual search tries to do matching over concepts. So it allows you to do things like match documents that don't contain any query terms, but still get pretty good results. There are two key challenges with keyword matching, or traditional keyword matching, that there's attempts to solve. One is polysemy, which I always have a hard time saying. Doesn't really roll off the tongue. This is where a word has more than one meaning. So picking some examples from our site, the term engineer on DICE itself is very ambiguous because without more context surrounding that, if someone just does a search for engineer, and people do that, we don't really know if they mean mechanical engineer, programmer, automation engineer. So that's one example of one term means many different things. The other problem is synonyms. So all of you will probably be familiar with this. You have many different variants of the same word, or many different words that have the same meaning. For example, QA and quality assurance, tester, those are all kind of have the same meaning. Or VB, VBNet, Visual Basic, they all have the same meaning. And so it's a kind of a challenge to make sure that you match across all of these common terms. And so conceptual search tries to solve this by mapping these terms into concepts and then matching on those concepts. It will also help you solve things like typos and common spelling errors, and also idioms, which are phrases that mean something very different to the words that are within them. Okay, so why conceptual search? Again, we will try to improve recall without diminishing precision. And this can match documents containing none of the query terms. I'm repeating this because that is really the thesis of this talk. So I'm sorry if I'm kind of repeating myself. Okay, so what are our concepts? They represent sort of high-level ideas in your domain. So in our domain, Java technologies or big data jobs, help desk support positions, those all kind of represent concepts that are important in a job search, in an IT job search. These concepts can be automatically learned from documents using some unsupervised machine learning techniques. And typically, It learns a set of concepts and a mapping of terms to concepts, where the terms have sort of a degree of association with different concepts. So a term can belong to multiple different concepts. As you might expect, for example, Hadoop may belong to both a Java concept and also a big data concept. So how have people tried to solve this in the past? What are some of the techniques that are used out in the literature? So a lot of you have probably heard of the term LSA or LSI, so latent semantic indexing. It's in the title of this talk. So that is one of the most popular techniques for doing this. LDA, latent Dirichlet allocation, I'm probably saying that wrong. That's used for topic modeling, which is a very similar kind of idea. And then Google recently released an algorithm called Word2Vec. And that's really what I'll be focusing on today for various reasons, which I'll explain in a minute. So all these algorithms work by mapping a document to a low-dimensional vector. That is a list of numbers. And each number in that list kind of represents how well that document represents a concept. Problem with LSA, LSI, LDA is that they're very computationally intensive to compute. They rely on factorizations of very large matrices. This is a very slow and computationally intensive process and requires a lot of memory. And this is a really important thing, if you want to use these in your search engine, you have to embed a very kind of hefty model into your search engine. And then as queries come in, you have to map them to this sort of concept space. So that is not easy. That has a big performance impact. And it is not really desirable if you want to get something up and running quickly in something like Solr. Query performance is very poor because documents are not represented by a number of terms which are unique to a subset of documents. They're represented by these kind of lists of numbers. So you can't use the inverted index in Solr to get fast document matching. So you can't really get the kind of good query time performance using these tools, which is why they don't scale well. That's why I believe companies like Google don't use them directly, as far as I know, because it just wouldn't scale well. So these traditional techniques work by learning a vector representation of a document. What I really want to do in order to use something like this within Solr is to map words, not documents, to vectors. And then rather than embedding those vectors themselves, do some processing so I can kind of use that information and get it into Solr itself. Why do I want words, not documents? Because Solr is very much based on kind of a word or token-based analysis chain. So I want to kind of use that to kind of bootstrap into getting this to work. Okay, so next couple of slides have a little abstract. So fair warning. Word2Vec was developed by Google around 2013. It learns vector representations for words. There's a link to the paper if you're mathematically inclined or like this kind of stuff. But basically it works by training a machine learning model to predict what words will come before and after a word in a document within a fixed window. So rather than requiring this very computationally intensive algorithm where you're condensing a matrix, it's just learning word by word. And it's much faster, which is one of the reasons Google built it. You know, they need stuff to work well, but it needs to work very fast. So you can give it a large amount of documents, and it will scale very well, unlike the traditional techniques. But the important thing is, once you train that model, similar words get similar representations. So you can then use that to kind of mine synonyms and related terms within your document set. So one of the interesting things people found when they did train this model is you could do what I would call word math. This is a little crazy that you can actually do this, but supposedly this worked when they trained it on a large model. So they trained it on something like Wikipedia, large data set. And they found that they looked at some of the vectors that they learned, right? And they tried to just do some very simple like arithmetic operations with these vectors. And they found one of the things that worked is if they took the vector for man, subtracted king, and added woman, it kind of mapped to queen. So what it means is it'll kind of learn this notion of gender automatically itself from Wikipedia data or whatever data set they trained it To give you another example, it also learned notions of capital cities. So it learned that there are these countries on the left and these capital cities on the right, and the difference in the vector space between them was very constant. So it's able to learn concepts automatically from just raw data. And it's supposed to be state-of-the-art or near state-of-the-art for sort of automatic word analogy tasks, like SAT verbal reasoning tasks. People have used it for that kind of thing. And it does very well for a machine. So at this point, and I apologize for this, you might be thinking, what's all this mathy stuff, right? What's this got to do with search? Why do I care? This is a search conference. Why are you telling me this stuff? Why are you doing this weird kind of word math stuff? Well, as I kind of mentioned, this algorithm can be used to represent documents as vectors or concepts. And we can use that to configure conceptual search. And we can do this by learning vectors for words and then learning which words are related to one another. And we can boost the recall, which, as I mentioned, was the main goal of this. One way you can think of this as a way to automatically learn synonyms. It's not really learning synonyms. The words, the similarities it finds are more kind of related terms. So a related term would be Elasticsearch and Solr. Those are not really synonymous, but they tend to occur a lot together, and they tend to be very related. So if you get documents on Elasticsearch, they're probably likely to be pretty relevant to Solr too. OK, so I want to give you a quick demo of this kind of working. So I have Solr running on my machine with a set of config files that run this conceptual search. So the first query I would run if I run data scientist. Okay, so this is a simple kind of search interface that runs on our DICE jobs site, our DICE jobs collection. And to illustrate how this is working, I'm explicitly excluding any document that matches any of the search terms. Because I want to know what documents I'm surfacing that our regular search engine will miss. Okay, so I'll repeat that. None of the matches here match those search keywords in any way, shape, or form. Okay, so if I search for data scientist, I get a lot of Hadoop jobs. I get Python engineer. Now, I'm a data scientist, but a lot of you here might not be data scientists. So Python is one of the main programming languages that data scientists like me use. So that is what I would consider a relevant match. And you see other kind of Hadoop jobs. And Hadoop is a big data technology, so a lot of data scientists use that. Then I search for a programming language like C#. I get kind of .NET jobs that don't mention C#. So I get .NET developers. I get VB.NET leads, .NET architect. This is a search conference, so I want to do a search at a search conference for information retrieval because I figure I got to do that, if I can spell it. OK, so if I search for information retrieval, what do I get? I get data science positions. I also get natural language processing engineer. These seem kind of relevant to my search term, even though these documents don't contain the words information or retrieval. Down here, I get machine learning specialist, machine learning library, text mining. Just to show this doesn't just work with tech jobs, I can do a search for project manager. I will get managerial jobs. Notice none of these have the term manager. They have the term managers or MGR. I'm explicitly excluding synonyms just for the analysis here. Normally, we would map those to manager, but I'm just using this to evaluate the tool. Also, if you search for director, you get a lot of development manager positions, and so on. So you can see that it's able to retrieve what I would at least consider relevant documents, even though those documents don't contain any of the search terms. Okay, so how do I do this? How am I making this work within Solr without using a machine learning model within Solr itself? So I provided a number of Python scripts that go along with this talk. And those Python scripts you can feed a large set of documents to, and it will do some sort of processing on the documents. It will try and extract important keywords and phrases, and then it will train the word-to-vec model for you. And then you'll have various options of what to do with that model when you've trained it. And this is really where to get to how do we ingest this into Solr. So I'm kind of heavily using the synonym functionality in Solr and kind of hacking that in some ways. So one method I'm going to use is I'm going to embed the raw vectors for the terms directly in Solr using a few plugins. I don't recommend doing that in production. This is more a proof of concept. It does not perform well in terms of how it scales. But if you really want the most accurate results, that's something you can tinker with and play around with. But to get it to scale well, I looked at some other approaches. So you can take the top n terms, where n could be 10, 20, 30, that it found that were similar in your document set. And you can extract those, and you can put them into a synonym file. But I don't just stop there. I use the weights, the similarity weights that the model has been able to compute in terms of how related it finds the terms within a document set. And so I use those to augment those sort of query expansion terms at query time so that it treats certain terms with a higher weighting than others. And you can actually do that with a little bit of tweaking with the synonym filter and a slightly modified query parser. Or you could just handle that in your API just as easily. And the last method to kind of inject this information into Solr is you can use a machine learning clustering algorithm. Take these vectors that you've learned for the words and compute clusters for them. And then for those clusters, you can map those to using the synonym file. So if you have a cluster that contains Java, and Java developer, you can map those to the same token. That is the easiest way to consume the output of this. So it's important for this to work that you have a set of important keywords for your domain. In the talk from Trey Granger earlier, he suggested using, as a starting point for this kind of analysis, your top search terms by doing query log mining. I would also advise that. That's a very good starting point to determine what words are important in your domain. But going beyond that, I've built a simple algorithm that will mine your documents for you and find commonly occurring phrases and terms. And you can also use those to learn synonyms over. So I've kind of just gone over that. It's important when you're doing this to take common phrases and map those to single tokens. If you just do it on a single word basis, you don't always capture terms like data scientist. One thing we found with our search is if initially searches for data scientists would produce a lot of scientist positions because it wasn't taking into account the whole phrase. So it's very important that you kind of configure Solr to extract tokens for these phrases when you're defining your keywords. So as I mentioned, you can do it yourself. All the code is now publicly available on GitHub. I will be adding documentation to that over the next few weeks, but I've already tried to document it enough to get you started. There's a set of Solr plugins. Some of them are to do with this talk, but as I mentioned, they do a lot of other things too. I have a repository for Solr config examples. The easiest way to understand how to use the plugins is to see an example of it in a config. Go there, you'll see the parameters documented in there. And then Conceptual Search repository, that contains the machine learning stuff. So that is all in Python. You just have to run Python on your computer and give it a set of documents and a set of keywords. Okay, so what additional tricks am I using to make this happen? So you can use the synonym filter in Solr to extract keywords from documents, kind of a primitive parsing. Or you can use the Solr text tagger. That will do the same thing. What that looks like is this. So basically, we're kind of hacking Solr here to sort of do simple kind of term extraction. So if you enter, you have a bunch of information like this. It's kind of noisy. Awesome Lucene position. We have a synonym filter configured with a set of important skills. It will then go through, oops, sorry, I just hit something very bad there. Is it sorry. mouse wheel by accident. If you configure your synonym filters with a set of phrases and terms, and then use a type token filter factory, you can use Solr to do sort of primitive term extraction, although it's actually quite sophisticated, so it'll always extract the longest matching phrase. Or as I mentioned, you can use the Solr text tagger to do this for you too. So as you can see at the bottom here, given that initial input, we've extracted the terms Solr, Lucene, Solr, Elasticsearch, and Zookeeper, and then kind of normalize them into these canonical forms at the bottom. And this is just using the standard functionality in Solr and the synonyms file. The second trick to make conceptual search happen in Solr is to make a use of payloads. So payloads are a very useful functionality in Solr. I think it's often very much overlooked. What they allow you to do is to tag each term in your document with a value. In this case, that can be a real number. Then you just need to make some small modifications to a similarity class and a query parser to allow it to use those payloads in the scoring functionality. This is very powerful. It has many applications beyond this. One of them being we use it in our recommender engine to weight terms in a document by using a custom weighting scheme. You could even use it to implement a simple machine learning algorithm within Solr, or model, a linear model, by allowing you to just basically set weights on terms in a document, rather than just use the TF-IDF values. So we use a synonym filter to expand a keyword to multiple tokens. And then we take each token, and it has an associated payload. And then we use that to adjust the relevancy scores at index or query time to make this kind of conceptual search happen. So you can think of this as a form of sort of query expansion. But you can do it within Solr at index time if you wish. You can do it at query time, or as I mentioned, you could do it in the API. So what does this look like in the analysis chain? So again, I'm using a synonym filter and a type filter to extract and normalize the term Lucene. And then the bottom here, you'll see the bit I'm now talking about. So there is a synonym mapped for Apache Lucene that maps to a set of top n terms in this instance. And each of those has a payload associated with it. And you'll see that payload with the pipe symbol. So first of all, it takes Apache Lucene, it expands it to the most related terms as found by the algorithm. And then it takes that payload, and then at query time, converts it into a term time boost, which you'll see down here. You can also do this at index time and just use a version of Edis Max, which is on my plugin site, that can also kind of read payloads and include the payload in the score. Okay, so what do some of these example synonym files look like? So I'm going to skip the vector-based method, but you can read more about that on the plugin page. But this is an example analysis chain for this kind of technique. So we just do some basic kind of pre-processing here to remove HTML characters and white space tokenize and stuff. Then we use this job titles file to sort of filter down the set of terms to a set of job titles. We then use a type token filter factory to remove anything that's not a synonym, so that's not in that file. And then we use a delimited payload token filter to extract the payload. And then I use this kind of these kind of custom token filter factories to then extract the term time boosts. So what does a file that you can output by this model look like that you would ingest in Solr in terms of a synonym file? So this is an example entry. Here I'm just using top n of 5, so you can kind of understand what it looks like. You might want to use larger values. So it's taken the phrase Java developer. Again, I've collapsed that into a single token, as I mentioned. Maps that to Java J2E developer, Java architect, lead Java developer. These are all terms that the algorithm has learned itself or relevant to Java developer. And then you'll see these different payloads. So these are in order. So the ones furthest sort of, or closest to Java developer or the most similar or related to it. As I mentioned, you can configure this at index time with payloads or at query time. If you do it at query time, that gives you a lot of choices because then you can play with different approaches, different field weights, and so on, without having to re-index. And I know for some people at least, re-indexing can be something that takes from an hour to weeks. So being able to configure this at query time is important, at least for some people. One of our sites, we have millions of documents, and so we cannot run many experiments where we have to keep re-indexing. So that's kind of important. Unlike the vector method and unlike LSA, we're still able to make use of the inverted index, right? Because we're just basically using this to do term expansion. So it's fast at index and at query time, as long as you don't set n to too high. So the last method I mentioned, instead of doing this sort of top n term approach, you can do clustering. And again, I have some code that will do the clustering for you in that GitHub repo. So what you can do is you can take this model, take the vectors that it's learned over your top keywords and phrases, and then you can cluster those by similarity. What you might want to do is, rather than just do one set of clustering, you might want to do several steps with different size clusters and combine those into different fields so you can give those different weights. So that the tighter, the smaller clusters have more weighting, because that is kind of a narrower basin of related terms. So what does a synonym file look like that's output by the sort of clustering approach? As you can see, these are all kind of terms within the same cluster. And so they just map to some arbitrary cluster token label within your synonym file. This is probably the easiest way to use this out of the box. You don't need any kind of custom payload functionality or anything. You can just kind of do this and then configure it in a synonym file, and you're done. I've not seen a noticeable impact on query or indexing performance. In fact, in some ways, it may actually improve it. So to try to understand the power of this algorithm, it helps if you kind of look at some of the clusters that it's able to learn from our jobs data. So I picked some examples from the first time I ran the algorithm. You know, there was no tuning or anything. This is just the first time I ran it to see if it kind of made sense what it was doing. So there was a cluster for what I would call natural language information. So it had bilingual, Chinese, French, fluent, speaker. These are all kind of terms related to natural languages that were all in one cluster. That is the entire cluster. I haven't removed anything. It made a small cluster for Apple programming languages, of which it found two, Cocoa and Swift. By the way, these labels here I have added for interpretation, but obviously trying to infer that is a little hard automatically. It learned a cluster for search engine technologies. So it clustered Solr, Elasticsearch, Lucene, search engines. They all came in the same cluster. And it kind of had a cluster for .NET. But beyond pure tech skills, it also did some interesting things. So another thing I found was it was able to cluster the terms that employees use when they're describing the sort of ideal candidate for a role. These terms kind of relate to sort of attention and attitude and focus. So produced a larger cluster of these kind of attribute-type terms where it's describing someone's attitude, which I thought was really interesting. So terms like pay attention, self-motivated, diligent, detail-oriented, they will all kind of map to that same cluster. And again, this is all automatically extracted by the algorithm. There's no supervised labeling going on here. You're not having to go through and do a lot of labeling of your data. It's learning like what terms are related in your data set for you. It's doing a lot of work without much configuration. So to summarize, it's easy to overlook recall when you're performing relevancy tuning. Conceptual search provides you with a method of improving recall while still hopefully maintaining high precision by trying to match documents on related terms, concepts, ideas. In reality, this involves using a machine learning algorithm that will learn what terms are related to one another. Word2Vec is a very scalable algorithm for doing this. It's very fast. It doesn't seem to use much more memory, even if you give it multiple times the amount of documents. And it's shown to do very well in word analogy tasks and mining similar words and so on. So it's an appropriate tool for this task. And there's a reason that Google developed it for doing this kind of thing. And we can train a word-to-vec model offline. And then we can take its output, pre-process it, and use that within Solr using various methods to try to make Solr do conceptual search without embedding some complicated machine learning model. And that requires, may or may not require use of payloads and custom plugins, depending on which approach you take. I would start with the clustering approach, because that's very easy, and then maybe experiment with some of the other ones, if that makes sense to you. So that is the end of the talk. I have about 5 minutes for questions. Yep, go ahead. Again. The guy there?
So the synonym that you learn, did you have to manually curate them after, or did you just use directly the output from the other?
So I used several approaches. So first time, and this gave the best results, I used a set of keywords that we defined ourselves. One of those was very simply a list of top job titles. That's very easy to define, but the skills have taken more work. But I also, and I include code for this, I also experimented with just taking a set of keywords and also extracting commonly occurring phrases, and also using that to train the model, and that still did pretty well. So that second approach didn't require any kind of manual engineering or determining of keywords or so on. So if I switch to keyword clusters here, it doesn't work so well for that one. But it didn't, like as I mentioned, it's not quite as good, but it still works pretty well. So if I type in data scientist, I get MATLAB positions. I still get some Hadoop positions. I get some kind of data-related positions. C# gives me a bunch of .NET positions. I got a little confused about ADO because that's a .NET technology, but it's also a server-side thing. But you're getting VB jobs, other things. So that works pretty well. Like if you don't have a set of keywords defined, then you can try this second approach. But I would definitely start with this kind of list of your top search terms. Like everyone should be capable of extracting that. If you want, you can run my algorithm to do the phrase mining and use those also. Yep, lady there. Mm-hmm. Mm-hmm. Yeah. So you have to be careful how you want to use this. Because sometimes if you show users documents that don't match the terms, even if they're relevant, they may complain, right? So it's important you test this. And also, when you're building a UI, you probably need to tell your users that, OK, this isn't an exact match, right? So you may want to offer this as an additional option. There's many ways you can use this. One would be as a different option, right? You haven't found any good documents, click here. A second would be just to call them out in the matches, and then use the QF functionality to weight this kind of lower than exact matches, so that once they start running out of good matches, then you start to see the conceptual matches. Yeah, just for the purpose of evaluation, right? But how I would configure this in production is I would set a high value on the phrase matches and exact matches, and then pull these in at a lower kind of weight. Another way you could do it is you could do a re-ranking functionality. So you could use the Solr re-ranking functionality. So you could take the top 1,000 matches, and then you could re-rank with this. So that if you only have like 1 or 2 terms that match, for those terms, if you configure it correctly in Solr, you could then make sure that, well, OK, I only match on 1 term, but I match on 5 related terms here, or 5 clusters or whatever, and rank those higher. So there's many ways you could use this. We're still kind of evaluating how we want to go forward. But we showed this to our recruiters, and they really like it because I didn't even think of this. There's a lot of tech jobs that are really hard for people to place. Like DevOps is extremely high demand right now. They're having a really hard time placing DevOps developers. This gives them like good suggestions as alternate types of developers they could find. So they don't find any good DevOps developers, although too expensive. This shows you really good matches that are kind of that would be a good DevOps developer. They would have a similar skill set. Currently, this is still in a kind of evaluation phase, but we do intend to use it on the site soon.
At one point, you said that your approach here wouldn't necessarily scale well, but it was accurate, and you had ideas about doing something useful. Hopefully, I've jogged your memory.
Yeah, sure. Sorry. So the approaches I focus on, I think scale just fine. Like I didn't notice any detriment. My initial idea with this, and I kind of avoided that because I think it complicates matters, is I actually tricked Solr into matching on vectors themselves. So you could take a term, and say you have for a given word, you have a 100-element vector. You can use synonym files and other stuff in Solr to map that to 100 tokens with payloads on them, and then do vector-to-vector matching that way. And then you kind of have something that's very much like LSA inside of Solr, but that doesn't scale well, and it's kind of complicated. So the code's out there if you look through and see how I do that. It uses the same concept, but rather than taking the top 10 or 20 related terms, those map to artificial kind of tokens, 0, 1, 0, 2, 0, 3, something like that. That are elements in the vector, and then the value of that element is your payload.
Your point is that approach is an alternative to this.
Yeah.
That does work.
Yep.
It may not scale very well, and your approach here will.
This scales well, yeah. So I mean, that's probably going to be the most accurate approach, but it has a big cost in terms of performance because you can't use it for inverted index. You could use it for re-ranking though, right? If you just re-ranking the top 100 terms or 100 matches or 1,000 matches or something. Lady there. I actually use jobs for this, and the reason for that is, so we have jobs data and then we have resume data. A job contains a single job. A resume contains a bunch of jobs. So the jobs are generally more focused. However, this word2vec probably wouldn't care because it's looking within a very narrow window around the word. But when I've used LSA on that, jobs definitely work much better because LSA is looking at what terms occur in the same document, where this is using a very kind of narrow window. So you could use it with I would say it's more flexible as well as scaling better. Does that answer your question? This one was just under 100,000. So I prune a lot though because we have a lot of ones that are really short. So after the pruning and pre-processing, I think it was about 66,000. But it runs pretty fast. So I have a lot of pre-processing steps, and so those actually take longer than a model to train, probably, like to do the HTML parsing. And all that goes in there too. I'm just using some open source libraries. The model training itself, I think to train 10 iterations took about 10 minutes. So it's pretty fast, and it's Python code. So there are implementations of it in Java and other libraries that are probably even faster. But it's pretty fast.
The attitude slide, right, where you have a long list of all the related terms to attitude.
Yeah.
Were those purely derived from co-occurrence in documents? Or I don't understand like how you got such a big list.
So I'm doing clustering here. So the cluster sizes can vary, right? They're based on just like the clustering algorithm just tries to find the most similar items, and you set a number of clusters. Some of them have 2 items in them. Some of them have a lot. So you'll find the larger clusters have a lot of very, very similar items in them.
There's no input, though. You're not telling anything what these words mean.
Right. So it's learning that by basically going through the documents and looking at what words occur close to one another,
Okay.
and then training them. Yeah.
So some might
It's
occur close to other ones, and then
yes.
not
Yes.
all have occurred all at once. But
Right.
they
Right.
cluster together naturally.
Yeah. I mean, it's sometimes it's like co-occurrence. Like you can get quite far by doing just a simple co-occurrence model with a window, which is what people have done in the past. But this uses a machine learning approach that probably produces better results, at least in the tasks they've done. But you can think of it as doing that. It's not explicitly computing that, but it is, in a sense, doing that. So you can read the paper if you want to know how it works. Yep.
During this process, have you observed any clustering that would have distortion that would be prohibitive, like a term that clearly didn't belong there?
So not all of the clusters are perfect, but But you're using this to sort of augment your existing search, not to replace it. So if you do that, I don't think you'll get a lot of bad hits. But yeah, the clusters, not all the clusters are quite as neat as the ones I showed you there. I do not want to provide everyone. I'm providing you the code, but I don't want to provide you the output algorithm because that would be too much, and I would get in trouble. But yeah, most of them made sense to me. Like most of them these are pretty good clustering of terms. You can always, if you have time, you can always go and inspect them and delete the ones you don't like.
When you do the clustering, do you specify a field for each document, or is it automatically grabbing all the fields within the document?
Well, right now I'm just processing the whole document as text. You could do separate training on different sections of the document. That might be a good thing to do, actually, and just train it that way. And then you can Solr allows you to configure as many fields as you want and as many weights. And so I typically take the advantage of if I could have several different fields and they may be more important, then just separate them out, and then I can always change it at query time. So yeah, I would definitely, if you have different fields that are more important, then yeah, I would do this. Actually, for the one I showed you, I used titles and skills separately. So skills were extracted from the job description, trained it on that, and then I have a separate title model, and it was using a combination of those two to work.
You mentioned earlier on that there is policing,
Yeah.
same thing has different meanings.
Yeah, multiple different meanings.
Throw off this whole concept, because what you end up with something like there would be he or she groupings that. How does that work out?
With this, well, I mean, there's several ways it can work out. I mean, one of the easiest ways to do this, and that's why I said it's important, is just to make sure you're extracting phrases, not just single words, because that phrase itself will help disambiguate those kind of situations. But the other way this kind of works is it's not just mapping, like for a given document, it's not just mapping one word to one cluster, it's mapping 1,000 or 100 words to different clusters, so that combination of data should help disambiguate the problem. Because you're using the whole document context, not just one or two words. This is more, I guess this is pretty better at solving the synonym problem, but people have found that that mapping of concepts just seem to help to solve the polysemy problem too. I'm not totally sure how, but you guy over there?
So on your demo, you had like a drop down. And
Yeah.
It looks like those different models you're using to search, or are they different?
There's different experiments around. So like the first one I showed you was using the set of terms that we'd already defined, and that worked best. But then the second one I showed you was using the clusters, and all those clusters I showed you were not using any kind of taxonomy or any set of keywords. I was just using the most commonly occurring terms and phrases in a document set, and extracted by the Python code I've put out there. That will kind of try to efficiently mine through your data and find phrases, which you can also do with the mgram filter. I mean the shingle filter in Solr too.
So is that like your documents that you're throwing in, whether it's the
Yeah. Yeah.
to word it back to create the model, right?
Yeah. So I give it. You can give it. Bare minimum, you can give it as a set of documents in my scripts, or if you just want to use it yourself, you just give it the documents. I would recommend including within that, like I said, those set of keywords, because you want to make sure that it covers those, because those are really important, right? But it will do reasonably well without that. But yeah, that's really those two things. I was experimenting with another approach where I was going to use the keywords and then find terms that are very closely related to them and use those as keywords. But that's kind of what this is doing anyway, so I kind of abandoned that. That guy over there?
Yeah, real quick comment. I mean, this is really cool because you don't have to make it perfect.
Mm-hmm.
There can be errors and stuff in there. As long as you have like a corpus of related terms that you can use sort of like a democratic type of ranking.
Right.
So machine learning typically has good numbers, but they're not perfect. But this is an example where you don't have to be perfect.
Right. And that's the great beauty of a search too, is you don't get pretty good results even if it's not doing a perfect job. And this kind of makes that better. I think she just gave me the signal that I have to leave. But what I was going to say is, yeah, what I really like about this is there's no manual maintenance of synonyms. Some of our sites, like the medical profession, like we have medical job sites, that domain doesn't change very rapidly. Like you don't get a lot of new keywords appearing, but in the tech job sector, we have new skills coming all the time. So we need something that can handle that and automatically learn that. I don't have time to go and create these synonym files constantly once a new skill comes out. Thank you.